Question number 1, well actually 1 and 3, it says compare the right hand and left hand derivatives to show that the function is not differentiable at the point P, and then it says find the points where f is not differentiable. And so if you look at that, I mean we'll do it algebraically in a second, but if you look at that, to figure out the slope, and I'll show you algebraically, but the left side of the function is, this is a piecewise function, but from x equals 0 to negative infinity, we're going to use the function or the mathematical relationship of y equals x squared. And then when we go x is greater than 0, then we're going to use y equals x. So now I don't know if you guys remember this, and I'll show you how we'll do it formally, but as we come around and we take the slope of the line for problem number 1, if we come from the left hand side, the slope is 0. If we come from the right hand side, then the slope is 1. Okay, well, let me show you that. But what they're trying to show us is that the left-hand side and the right-hand side are not the same, so we don't have a two-sided derivative, right? And so it's kind of like limits in the sense that you need the left-hand side and the right-hand side. So let me just draw this out real quick, and then we'll do the math. So we have our xy plane. This is problem number 1. And we are going to represent this part of the graph with y equals x squared. And then we're going to represent this part of the graph with y equals x. And so to take, and what's our point of interest is 0, right? Because that's where the two join. So what we're going to do is we're going to take the limit of this thing as h approaches 0. So we say the limit as h approaches 0 from the negative side, right? Negative infinity, right? And positive infinity, right? So we're going to take the limit also as h approaches 0 from the right hand side. So the way that the textbook has this written is we would do it like this. We would say f of 0 plus h minus f of 0 all over h, right? Well, for the left-hand side, we use x squared, so this would be equal to, well, what's 0 plus h? H. So this would just be h squared minus, now what's f of 0?
Wait, where'd you get it? Where'd you get the square? Did you forget to put it over there? Did you just pull that
Wait,
square?
are we talking about right or left in there?
This is the left, right?
Yeah.
Yeah, but where'd you get the squared from?
Because we're approaching from the left.
Yeah.
Oh,
And so we're using x squared, right?
so is it f of 0 plus h?
Yeah, so you got to, you got to remember, so like where does this, so this is 0, right? But what does it mean? So if I say f of x equals x squared, then f of 0 plus h is equal to 0 plus h squared. But I'm just evaluating what we're skipping the middle step. Well, what's 0 plus h? Just h squared.
So did you not write the squared?
All she's asking is if there should be a squared right
No,
after.
there shouldn't be here.
Y equals x squared, you're putting 0 plus h in for x.
Because the
So it's
function
now
is x
0 plus
squared.
h. 0 plus h is h.
And then you put it.
So now when we say f of 0, if f of x is equal to x squared, then f of 0 would be equal to 0 squared, which is finally equal to 0. So that's where those terms come from. All over h. Well, one of these h's cancels with this h, and so we're left with just h. Well, what is h?
As opposed to 0.
So it's 0. So the slope on this one is just 0. Now we're going to do the same thing here. It's still written the same, but we're using different equations. So when I say f of 0 plus h, minus f of 0. What I'm really looking at, remember this is the slope formula. I'm really looking for y sub 2 minus y sub 1. Okay? Well, how do I get those answers? Well, I could write it over here. I could say f of x is equal to x, and f of 0 plus h is equal to f of, or not f of, just 0 plus h, which is just h.
I still don't get why you didn't square that one.
I did.
But it doesn't say it's.
She's wondering why you didn't square it right after the parentheses.
Well, because this is the function notation.
To me, he did it up there in the.
I know, but why wouldn't you, why isn't there a squared sign and then it says equals h squared minus 0?
Because this is saying the function evaluated at 0 plus h equals 0 plus h squared. So I don't square the function has a square in it. So this represents the function, this represents the value.
So the f, the f is pretty much saying, does the f replace the squared?
Well, because
When you write f of 0 plus h, is that the same thing as writing 0 plus h squared? You're just putting an f?
Yes.
Okay,
Yep.
that
Yep.
makes
We
sense.
just skipped a middle step.
Cool. Thanks, bud.
You're welcome. So now this one is just going to be h, okay, minus 0, right? Because if f of x equals x, then f of 0 is equal to 0. So then I've got h over h, and when we minus 0 means the same thing, so the whole thing reduces down to 1, right? 1 over 1 is equal to 1. So this is my left-sided limit, this is my right-sided limit. Why? Because here we're approaching from the left-hand side, and this one we're approaching from the right-hand side. Because we're approaching from negative infinity, so we're coming along the curve this way. This one we're approaching from positive infinity, so we're coming this way. So it's not differentiable. We did all that work to show or prove algebraically that it is f prime of 0 does not exist. Now it's differentiable everywhere else except for x equals 0. Does that make sense? Now, if for some reason this function had a derivative of 0, in other words, if this derivative equaled 0 and this derivative equaled 0, then it would exist. If this equaled 1 and this equaled 1, then the derivative would exist. If this was a smiley face and this was a smiley face, then the derivative of the piecewise function would be a smiley face. Now that doesn't mean that this derivative, this one-sided derivative, is bad necessarily. We might be able to use that for something, and that doesn't mean that this one-sided limit is bad. We might be able to use it for something. But if we're trying to study the behavior of this graph at 0, we can't be very confident of it being the derivative. In other words, we can't determine the rate of change. So think of that in practical terms, right? Mr. Adams is evaluating a stock on the stock market. In order to model the behavior of the stock, I use a piecewise function. Because of the piecewise functions that I use, I'm interested in the rate of change. How much does the stock change? Does it increase? Does it decrease? When does it increase? When does it decrease? How much does it increase? Well, all those terms are nothing more than slopes or derivatives, right? So if I have a point in my piecewise function that's not differentiable, well, then the information is not reliable. So if this represented like some sort of stock or trend in business, I could look at it up to 0, and I could look at it from this direction up to 0, but I can't be guaranteed of what the rate of change is. So if I assume that the rate of change is 1 because my rate of change to the right is 1, and I do some sort of business based on those figures, well, it's possible that it might be 0. So I can't be 100%. However, I could be a lot more confident if both of them were equal to the same. Does that make sense to you guys? So you normally, graphically, when you look at this, it's going to be based on the fact, it's going to be some sort of cusp or corner, but there is definitely an abrupt, stark change in the slope at that point. If you go a little bit to the left, it'll be, for example, if I go a little bit to the left, I have a negative slope. Here, if I go a little bit to the right, I have a positive slope. And then algebraically, you can solve and figure that out.